Hello everyone, my name is Milton Yutaka Nishiyama-Jr. from the Laboratory of Applied Toxinology from Butantan Institute in Brazil. And I'll talk about the work on Ensemble AI model for prediction of antiviral peptides and their mechanisms of action. Nowadays, the infectious disease in an era of global change is increasing, and the last century has witnessed a wave of severe infectious disease outbreaks. So based on that, we are looking for drug discovery to identify new bioactive molecules, and using the advance of high throughput technologies has allowed us to find, especially based on the transcriptomic data from venomous organisms. So based on that, we have identified different approaches for antimicrobial peptides since 2007, and has increased the number of approaches, but they just predict the bioactive peptides from different ways, different computational models, and different efficiency or accuracy to identification and the validation. So based on that, we are proposing a new model that can predict the bioactive peptides as antiviral, and especially to predict their mechanism of action based on the membrane, replication, and the assembly process of the virus. So this is our model that are separated in two stages, and the first stage is the antiviral prediction. That's based on a ensemble model. We're using a neural network model and a random forest classifier. So the random forest uses different physical-chemical characteristics, and the neural network uses only the sequence of the peptide. So after the classification, the integration of the results of the prediction, we have the potential antiviral peptides, and we pass to the second stage for their mechanisms of action classification. So in the assembly, membrane, or replication action. So based on that, we have the two approaches. For the prediction, we have created a bigger positive and negative database for training validation tests compared to a database from older approaches, and we have selected different descriptors and characteristics to use in the model, and we have made some combinations and optimization to identify the best physical-chemical characteristics to be used to classify and to predict the antiviral peptides. And for the classification by the mechanism of action, we have tested different models, and the support vector machine has obtained the best performance, and we have made an optimization of the hyperparameter and created a balanced data for the classification based on the approach one versus all training using the optimized parameters. So based on that, we have compared our predictor with different other methods to prediction of antiviral peptides, and we have obtained, based on the public database, we have good results of sensibility, specificity, accuracy, and Matthews correlation. So we have created a greater and bigger database of validated and experimentally validated bioactive peptides for antiviral, and we could compare with 5-API method where we trained it, and we could predict the new antiviral peptides, and our approach has obtained very good, similar or better results than API. So based on that, we have proposed a new method that's an ensemble for the prediction based on machine learning and deep learning models. We have selected the appropriate descriptors and made us a feature selection and optimization to improve our method. So the NLP class approach is the first one to classify the AVPs based on their mechanism of action. So I would like to thank all my groups and students, especially Fernanda Bucal and Caio Castro, that developed this method, and for our collaborators and foundations that support our work. Thank you very much.